Our final talk from this session will be Nick Roberts telling us about mixed blocks for storing more fields flat.
Hi, thanks for coming to my talk. My name is Nick Roberts. I work on the OCaml compiler at Jane Street. Everything I talk about in this talk, a version of it is available in our branch. Sorry. Right. So I will be talking. I will be talking about an extension to OCaml's runtime representation of values that gives the programmer more control over memory layout and therefore more control over performance. The name for this extension is mixed blocks, and the basic idea, I'll give it away at the beginning, is that the heap objects tell the garbage collector which fields it should scan. Not exactly revolutionary, but there's some ideas here that I think will be interesting, or maybe interesting to the OCaml community. And there's certainly more to explain there, and I'll get there shortly, but let me start by saying a few words of context. Mixed blocks fit into Jane Street's work on unboxed types, which is kind of like a kinding system for OCaml that lets the user avoid automatic boxing of numeric data, among other things. Mixed blocks, the topic of this talk, relate to unboxed types, but I'm not going to be talking about unboxed types in this talk. I'm only going to be talking about the parts of mixed blocks that are a small diff, both like conceptually and in the actual implementation, against the OCaml that users are already familiar with. OK, so let's begin. How does memory layout affect performance? Well, I mean, it does, but many ways, the focus of this talk will be on indirection, kind of similar to Ron's question, actually, at the end of Richard's talk. Right, so and by indirection, I mean layers of pointers that code needs to follow in order to access the data of your data structures. And more layers of pointers means more work is expended, both by user code in order to compute with the data, but also by the garbage collector in order to traverse the heap and accurately track liveness of values. Right. Before I get into the rest of this talk, I'm going to walk through a quick example of the runtime representation of an OCaml value. I think many people are familiar with this already, but I think it'll still be useful to walk through. Right. So this record R here is a record of 3 fields, 2 of which are 64-bit integers in 64. And here's a schematic of like how this is actually laid out at runtime. There's a lot of detail in this diagram, and most of it's actually irrelevant, but I will draw your attention to the large number of boxes and the large number of arrows. There are lots of pointers in this representation. There's a lot of indirection. Each int64 value actually ends up being represented as a pointer to a 3-word heap object that consists of a header followed by like some generic operations, followed by the actual 64-bit payload of the object. And then R, the 3-field record, is this 4-word heap object with pointers to the int64 objects. This ends up being 10 words. That's kind of, it seems gratuitous. The thing I'll be talking about here, just to preview what mixed blocks look like, sorry. Yes, to preview the mixed block representation, you could imagine laying out the object something more like this, where the raw numeric payload is stored directly in the object. And this would take less memory to lay out. And just some terminology that I'll introduce. I will say that the I1 and I2 fields here, I'll get to the syntax later. I'll say that they are stored flat in the object. That just means that the numeric payload is stored directly rather than being a pointer to a heap object. And I will also call this a mixed block because it mixes pointers, like the pointer to the string s, with these fields that are stored flat. And the exact challenge of this I will get to shortly. Actually, immediately. The challenge with storing a field flat is the garbage collector must be told about it. in particular, it must be told not to dereference it and treat it as a pointer. So let's look at OCaml's prior art to understand this challenge more. It's already the case that OCaml stores some numeric fields flat. If you write a record that all of its fields are floats, that ends up, the float values are stored flat in the heap object. And the way that this is okay from the garbage collector's perspective is the tag in the header word of the object conveys that the object is a flat float record, and thus the garbage collector should not look at the fields. The fields, they might actually just look like a null pointer, for example, and that's one kind of pointer that the garbage collector should certainly not dereference. Yes, but this prior art is not enough for our purposes, or is not enough to kind of encode all the shapes of heap objects that you might want. The kind of current situation is that the garbage collector interprets a tag to mean either that it should look at all of the fields of a heap object, or it should look at none of the fields. This is all that is available in the current interpretation, with like a finite number of, like a very small number of exceptions. Yes, and what you might reasonably want is such an object as this, where the first field must be scanned. It is a pointer to a string. We must know whether or not that string remains live or not. It might be important to the user's use case that the remainder of the fields are stored flat so that they require less indirection to access. That is, you might want some mixing, hence mix blocks. Okay, so I'm going to talk about our design. As I alluded to at the beginning, it's not like especially revolutionary, but there's still some ideas that might be interesting, and this might be something that people might be interested for their own applications. Yes, so the design that we have implemented is one where unscanned fields can't appear, where unscanned fields can't appear prior to fields that the garbage collector must scan. So raw numeric fields can only be stored in the suffix of the heap object. And to implement this, we use the header word to encode the length of the prefix of the heap block that should be scanned by the garbage collector. This new data in the header word is effectively an encoding of this variant here, where the first constructor uniform is the old kind of backward compatible meaning, and the mixed constructor is the new thing. Happens to be in our design, and this may preview how many bits we have stolen to make this work. Only up to 255 scanned words before, in order for something to be allowed to be encoded in this way. Yes. So I guess the draw of this approach is it allows us to support mixed blocks without needing more space. Like, we don't actually need to make any heap object take up more space in order to support this encoding. Certainly, some questions arise. I guess one question is, do we even have enough room in the header to accomplish this? On 64-bit systems, the answer is like clearly yes. So let me tell you a bit about how this works. So what we end up doing is we steal a byte from the header word in order to encode this length. The current kind of layout of the header word on existing OCaml is the bottom byte is used to encode the tag. This is the byte that that conveys the information I said before of whether or not the garbage collector should scan the fields. It's also what's used to distinguish between the constructors of a variant. The next 2 bits are some garbage collector metadata. That's not actually relevant to this presentation beyond the fact that we are deprived of these 2 bits. Finally, the remainder of the header word is used for the size and words of the object. So if we steal 1 byte from that, we reduce the kind of expressible size of OCaml values from 4 petabytes to 512 terabytes. With either of these, the runtime system would have quite a bit of trouble even initializing the value in the first place, so this is clearly just fine. Yes. So the thing that we will use this byte that we've stolen for is to encode the length of the scan prefix +1. The only reason we do the +1 is so that we can use 0 as a sentinel value, meaning that the block is uniform. This backwards compatible meaning where either all fields are scanned or not. Yes. Okay, so there's, just to walk through a quick example, here is the example from before. The thing that we encode as the scan prefix length +1 is 2, because there's one field that is scanned. And on like kind of the old style of object, its header actually ends up looking exactly the same as before, because the top byte remains 0. This sentinel value meaning uniform. Yes, so certainly there are some things to talk about with this design. One advantage is that the scanned fields remain immediately after the header. The scanned fields are the ones that the garbage collector is going to have to dereference and traverse anyway. So it's convenient for the reading of the header, which the garbage collector does, to also load the scanned fields in the same cache line as the header. It would be silly to put the unscanned fields there because then they would be loaded for no reason whatsoever. Yes, so this is friendlier to hardware caches. Another kind of nice thing is that we've made the scanned prefix length logically separate from the tag. Pattern matching code that just cares about what constructor of a variant that it's looking at merely needs to look at the tag. It doesn't also need to care about the scanned prefix length. Further, we can allow any constructor of a variant to be encoded as a mixed block. That doesn't affect pattern matching. Yes, and there's an obvious limitation, which is like, I claimed that these were called mixed blocks, but certainly it seems to be a very limited class of mixing, where it's all like scanned things followed by unscanned things. You can't have an object where, say, the first and fourth field are scanned and the remainder of them are not scanned. Yes, and this is different than the approach that Haskell takes, where it actually allows for like kind of richer kinds of mixing, but this comes at the expense of requiring kind of more space in the representation of the value to encode which fields are scanned and are not. Like, I think for some values, Haskell, for example, just has like a bitmap of like which, like a raised bit indicates which fields the header should scan, and this kind of takes more memory. The advantage of our scheme is that we haven't actually increased the size of an OCaml object in order to do our encoding. Yes, and then another limitation, which might be a bigger limitation for some use cases than others, is that we don't support generic comparison over an object that has these unscanned fields. You can come talk to me afterward if you want like a detailed example of why this is difficult, but just for like kind of a flavor of it, imagine that your field encodes like two 32-bit floats. There you might want the like 0 and -0 to compare as equal, even though they're in like separate halves of the word. Don't worry if that was confusing. I said it very quickly. But in any case, the takeaway is that comparison is difficult to, maybe just impossible to implement. This happens to be okay for the style of programming used at Jane Street, where we avoid generic comparison in favor of PPX-derived comparison functions, but it might be more of a limitation for other use cases. Yes, let me talk about the syntax a little bit. Right, so like we've defined a new type, a new shape of object. How do users get the new representation? One option would just be to silently give it to people. Like if you use int64 as a field of an object, maybe now suddenly the field starts being stored flat in the object. We've decided not to do this and instead opted for a style where the user explicitly requests this shape of object. There's a couple reasons for this. one of them might be, well, users may have written external C code that is tied to the actual runtime representation of values. Also, if fields continue to be boxed on projection from the record, it's not always going to be an optimization to remove this boxing. It should really be a user choice. And then also, I don't know, it's nice to be explicit about what memory representation you're actually getting and the performance characteristics that you want. And aside, this isn't actually the syntax we've used at Jane Street. There's like, the syntax that we use fits more into like the whole system of unboxed types, so doesn't really fit in this presentation, let alone on this slide. Yes. We don't currently, it is currently the case in our implementation that the order that you declare the fields matches the order in the runtime representation. This means that we have to statically reject some ordering of fields, but this isn't like inherent. You could imagine, having the compiler actually pick the order of the fields that allows allows the value to be representable. Yes, I've done kind of a silly micro benchmark, but just to drive home the fact that indirection is slower. What I've done in this benchmark is I've varied the number of fields of type B that are marked as unboxed, and just run a benchmark where in a loop I've summed up all of the fields of such objects. You might be surprised that this runs faster because I just said that fields are boxed on projection. The reason why this doesn't end up affecting this benchmark is that because I'm immediately computing with the thing I've projected, a compiler optimization can remove the need for the box and just add the raw bits of the float of here, the int64, into the accumulator. So yes, indirection is slower. Another application that is maybe interesting is there's actually another kind of subset of values in OCaml. I've already talked about ones that need to be scanned and ones that need to not be scanned, but there's also ones that need not be scanned, that are fine to look at, but that you don't have to. And for those, again, this syntax doesn't actually exist, but you could imagine being able to mark those, and which would tell the garbage collector that it doesn't actually need to traverse those fields. The reason you might not want to do this is if you care about generic comparison. So it's not something that you should blindly do. Yes, and in fact, if the garbage collector doesn't look at a field, it is faster for it to do its work. Not surprising, but it is nice to see a kind of a line that goes all the way to 0. Yes. Yeah, and there's some related work that you might be interested in. That's all I have. Thank you for your attention.
We have some time for questions.
Thanks. What kind of types can you flatten? So you showed us in 64. I guess an array wouldn't be able to be flattened, but in the middle, what can you do?
Yes, so the types that we support flattening right now are kind of the numeric types, so int64, int32, float, native int, I think. Yes, those are all the ones that come to mind. I think it could probably be extended to more kinds of types, but those were the ones that we focused on for this. Yeah.
Thanks.
Nice work. I'm wondering if you've done some sort of real-world comparisons on the GC scanning performance and how often you can use this encoding to sort of speed up the GC.
Yes. So yes, I didn't mention this, but users have actually started using this feature in production. I think the performance we haven't seen any case where someone has come back to us and said, oh yeah, my program's running 5% faster or anything like that. I think for what we've seen so far, people have reported more modest speedups, 1 or 2%. But I think for a hot loop of code that you're really trying to optimize, this kind of technique is invaluable. Yeah.
Thank you.
Thanks.
So this is very nice for integers that are boxed, and we can represent them unboxed. Another place where I usually find these lots of indirections in programs is when you have nested records. Do you imagine it would be possible to sort of inline or fully flatten records with some annotations, especially if you add the reordering?
Sure. I think such a thing could probably be implemented even in the absence of the things that I talk about in this talk. If you're just thinking about like kind of like inlining the fields of one type definition into another type definition. But yes, I think in conjunction with the ideas here could allow for like this idea to carry, you know,
Yeah, you
carry
probably
through
need
that
the
idea.
reordering as
Yes.
well to make it.
Yes, yeah, with the yes, for something like that where you inline one record into another, yes, like the reordering becomes more essential. Also, if you wanted to represent modules using this same thing, because they're, you know, if you, well, this is too complicated of an example, but like modules are another case where kind of the reordering is essential to make it usable for users. Yeah.
Thank you.
Thanks.
Okay, let's thank the speaker again.